All right, hey guys, welcome back to Cougar Chem Tutoring. I'm Austin, and I'll be running through part 2 of problem set 7, quantum mechanics. Number 5, how does the concept of an orbit in the Bohr model of the hydrogen atom differ from the concept of an orbital in quantum theory? If you remember from the Bohr model of the atom, we had these like n shell orbits that kind of looked like planetary orbits around this proton. Okay, and we had this n equals 1, n equals 2, n equals 3, and n equals 4, right? And we would put like an electron here, an electron there, an electron here, and there. Okay, but in the quantum theory, right, we were talking about putting these in clouds. And the biggest difference here is that in this cloud, the reason that we can't really know where it is at any one time is because the electron is acting as a wave. It's acting as a wave here, okay? It's not, we kind of detect it everywhere because it's kind of everywhere at the same time. It's a wave. And unlike a particle, right? A particle can't be in more than one place at one time. But if you notice a wave like this, okay, it's both here and here, right? And it's hard to understand that, especially with something that has mass like an electron. But that's the biggest difference, is how does the concept of an orbit differ from the orbital, is that this deals with it in terms of a particle, okay? The Bohr model. Bohr model it talks about it more in terms of a particle. Whereas the quantum theory talks about electrons as wave. Electrons, I'll say this is the electron. Electrons as waves, okay? And they're kind of found in these clouds that we call orbitals, okay? So when we look at an orbital, if you were to ask where is the electron is the orbital itself, okay? It's creating this area of space that we consider the orbital. And we call it mostly like a cloud, okay? A cloud of space to find the electron, okay? To find electron. Okay, so that's the biggest difference. Trading as waves here, as particles here, and this is mostly as a cloud, where this is mostly as an orbit, okay? All right, part B, how many quantum numbers are needed to identify an orbital? How many are needed to uniquely identify an electron in an atom, okay, and why is there a difference? So back to the Schrodinger equation, remember we got these 3 quantum numbers out. These 3 quantum numbers will only identify one particular orbital. And the reason that we do that, so I'll say orbitals, we need 3 quantum numbers, okay, quantum numbers. And I'll just put in parentheses n, l, and m sub l. Okay. Now, what these signify is here, this is the shell. I'm going to say shell. We'll get to these here in a second in number 6, but n is the shell and l is a subshell. Okay, subshell. And this is the actual orbital, okay? And in particular, it defines its orientation. Because there could be multiple orbitals in one subshell, and they'll all have different orientations, and one will have a particular orientation, which is what we designate as m sub l, okay? So we only need these 3 quantum numbers to identify an orbital. Now, the thing with an orbital is that 2 electrons occupy any one orbital, okay? So in order to determine to identify an electron using quantum numbers, we actually have to add one more quantum number to that, okay? And we call it the spin quantum number, and that's going to be m sub s. So I'm going to say electrons, 4 quantum numbers, okay? And in this case, we'll say n, l, m sub l, and m sub s. Now, this quantum spin is designated by either positive 1/2 or negative 1/2. Okay, that just means either upspin or downspin. Okay, and any one orbital or any one region of space, okay, within a subshell can hold 2 electrons. Okay, so that's why we have to differentiate. The one electron will have an upspin, and the other one will have a downspin. Okay, so that's the difference is because those electrons have spin, and technically also have different energies. The upspin is actually lower in energy than the downspin. And so we have to designate which one is which. All right? Okay, number 6, for the 4 types of quantum numbers, give the name of the quantum number, its letter, symbol, and range of possible values, and explain in 1 to 3 sentences what property is related to each quantum number. Okay, so let's start with the first one. Okay, the first one is n, right? N is what we call the principal, I'm going to say principal quantum number, Okay, we often refer to this as the shell, okay, the shell. So when we said n equals 1, n equals 2, n equals 3, we were talking about shells. We were talking about these principal quantum numbers. And as you increase shells, right, as you go from n equals 1 to n equals 2, and so on and so forth, you're increasing your energy, okay? So within these shells, we'll see that we also have subshells and stuff like that. But as far as rules for these n's, they can only be positive integers. Only positive integers, okay? Starting at 1. Okay, so I'm just going to put n is greater than or equal to 1, okay? So those are the rules. Remember, we don't have an n equals 0, so we're starting there, and we can't have an n equals 2.5 or anything like that. It's all whole number integers, and they're all positive, okay? And this corresponds, we'll just say corresponds to energy level of the electron, particularly the shell, okay? That's the main thing. All right, number 2. L, okay, this is what we call the angular quantum number, angular quantum number. And in fact, you actually may hear this called the azimuthal quantum number as well. So either one works. So I'll put quantum number. And this is considered the subshell, okay, subshell. So this is referring to like in the periodic table, we have, it's kind of split up into blocks here. Okay, this is not a great picture of it, but here we've got the lanthanides and actinides here on the bottom. Okay, this side of the periodic table, okay, where these are, this is called the S block. Okay, and the S block, the S is a subshell. Okay, then over here we have the P block. So this is the P block, this is the D block, and this is the F block. And each of these are a particular subshell within the shell. Okay, so for example, you can have a 2s subshell, but you can also have a 2p subshell. So and they'll have their own orbitals and such. Okay, so that's kind of what we're thinking of when we're talking about subshells. Okay, you can still have 2s and 2p, right? They have the same principal quantum number 2, the same n, right? They're both in n equals 2, but they have different subshells. They're in slightly different energies within that shell. Okay, now the rules for this one is it can only be up to in positive whole number integers starting at 0. I'll just put 0, 1, 2, ... up to n minus 1. Okay, so it can never be the actual n. So if we had an n equals 5, our values for L could only be 0, 1, 2, 3, and 4. They couldn't be up to 5. Okay, so we just have those. All right. And this corresponds to, I'll just put it down here, corresponds. The shape, okay, to the shape of the orbital. So remember earlier I was saying that this orbital up here was an S, what we called an S orbital, okay? That's because it's found in the S subshell, okay? So the shape, okay? So we have energy level, we've got shape, and then 3, we've got what's called M sub L, and it's called the magnetic quantum number, magnetic. There's quantum number. Okay, and it gives us the actual orientation of the orbital that we're talking about. So I'll just put, well, let's talk about the range first. This ranges from negative L to L in integers. Okay, so let's say L was equal to 4. Okay, that means M sub L would be limited to negative 4, negative 3, negative 2, negative 1, 0, 1, 2, 3, and 4. Okay, or so on and so forth. If it was just, let's say L is equal to 2, then we would only have this range right here, right? So stuff like that, okay? All right. And then that corresponds to, so we said that corresponds to orbital orientation, And in this case, the specific orbital. I'll just put specific orbital. Okay? All right, last one. We talked about this one here in the last problem, but we've got the magnetic, or the spin quantum number. Spin quantum number. Okay, and that's just designating either upspin or downspin. So let's designate, it can only be negative 1/2 or 1/2 or positive 1/2. Okay, corresponds to upspin or downspin. Okay, and this is particularly for just electrons. Okay, just electrons. All right. Okay, number 7. So putting this into practice, Okay, what are the possible values of quantum number L when n is equal to 5? All right, remember that the rule is that L can be up to, in positive integers, up to n minus 1. So that means L can be, we'll start at 0. Okay, it can be 0. It could be 1, it could be 2, it could be 3, and it could be 4, but it cannot be 5, right? It can't be equal to 5, up to n minus 1. Oops, not n equals 1, n minus 1. Okay, so this would be our answer for 7a. 7b, which are the possible values of m sub L when L is equal to 3? Okay, so remember that m sub L is from negative L to L in positive in integers. Okay, so if L is equal to 3, this one's really easy. It's just m sub L is going to be negative 3, negative 2, negative 1, 0, 1, 2, and 3. And this is our answer for that. Okay, so m sub L is just going to mimic the L just in integer form in both negative and positive directions. Okay, all right, last one, number 8. Which of the following sets of quantum numbers are actually possible? If a set of quantum numbers is impossible, explain why. All right, so A, remember that it's in this order, so we've got n, L, m sub L, and then m sub s. Okay, so we've got n is equal to 4, L is equal to 4, m sub L is equal to 3, and 1/2. Okay, firstly, this L is equal to n, right? We can't ever actually equal n. We can only go up to n minus 1. So I'm going to cross this out and say L cannot be equal to n. Okay. So other than that, if this had, let's say this had been a 3, okay, these would actually be valid quantum numbers, but they're not. Okay, letter B here. N is equal to 5, and L is equal to 4. Okay, so that should work. And negative 4, yeah, m sub L, this is m sub L, right? And it's equal to negative L to L, and that's negative 4, yeah, that totally works. And then negative 1/2, yeah, that's totally valid. So I'm going to circle this. That's totally good. All right, C, looks like we have the same problem, right? We got L is equal to n in this case, so I'm just going to cross it out and say L cannot be equal to n. All right, D. We got 3, okay, n is equal to 3, okay. 0, that actually works, right? We can, with L, we can start from 0 and go 1 and 2. Okay, that would be our possible values when n is equal to 3. So yeah, 0 is one of those values. And then it says 1. Remember, this is m sub L. M sub L is equal to negative L to L. But if L is 0, then we could only have 0, right? And so this is actually not valid. So what I'm going to say here is m sub L cannot exceed L. Okay, we've exceeded L, we're at 1, we've gone over it by 1, it's just not going to work. Okay, and last one, n is equal to 2, and L is equal to 1. Okay, that still works. And then, oh, we have the same problem. 2, this exceeds now the 1, right? In these values, if L is equal to 1, then m sub L could only be equal to negative 1, 0, and 1. But in this case, they put 2. So I'm going to cross that out again and say m sub L cannot exceed L. All right, I hope that was helpful for problem set 7, quantum numbers.